Our goal is to now proceed to construct many measures on sigma fields. We've successfully constructed a few measures, largely discrete. The reason that we haven't been able to go further is that in most cases, the measure of a set is going to depend fundamentally on the structure of that set. And the subsets of a space like the real line are fierce indeed. Sigma fields contain very wild sets, and it's very difficult to describe their structure. Therefore, in order to construct measures, we need to start small and expand later. We're going to reduce our goal from constructing measures on sigma fields to constructing measures on fields, closed under complement and finite union, but not necessarily countable union. And later, we will understand how to extend those objects to full-fledged measures on sigma fields. Let's be precise. Given a sample space omega and a field, or algebra, that pair is denoted a premeasurable space. A premeasure is a function on the field, taking values in the positive reals and infinity, that is countably additive. Now, let's be clear about what that means. Since the field is not automatically closed under countable union, we have to be careful here. What countable additivity means for a premeasure is as follows. If I have a countable sequence of sets in A, happen to have the property that their disjoint and their disjoint union is an element of A, which of course can happen, it's just not forced to all the time. If we're in that happy circumstance, then this function mu is assumed to be additive on such sets. That is a premeasure. Premeasures are much easier to construct than measures because fields are much easier to understand than full sigma fields. Nevertheless, this countable additivity constraint can still be challenging to satisfy. And so we'll go one step even lower. And we will first start to construct finitely additive measures, which are functions defined on fields in the same fashion, but where we only assume finite additivity over disjoint unions instead of countable additivity. Now these, in many cases, will be fairly easy to construct. That'll be the main point of today's lecture. In order to distinguish them from their countably additive cousins, let's change notation and use the letter chi to denote finitely additive measures. Our eventual game plan will be to start by constructing finitely additive measures on fields, then show that those finitely additive measures are in fact countably additive and therefore are premeasures on those fields under conditions that we'll determine, and then show that we can extend those premeasures on those fields to fully fledged genuine measures on the sigma field generated by those fields. That last step is going to be the hairiest, but let's start with the first step, constructing finitely additive measures on fields. Before we construct some, let's make sure we understand some of the properties that they have and how they might differ from the eventual objects we want to construct, genuine measures. Here is one comment which we'll see later on can really show the difference. Suppose that we have a finitely additive measure space. That means we have a sample space, a field of subsets, and a finitely additive measure on that field. Let's try to test for countable additivity to see if this finitely additive measure is actually a premeasure. Well, it turns out that we're always halfway there. The theorem is that if I have a countably infinite sequence of disjoint sets in the field A, and it so happens that the disjoint union of those infinitely many sets is back in A, meaning that we can use the countably additive measure to measure that disjoint union A, then that measure might not be equal to the sum of the countably additive measure on the pieces, but it's always at least as big as that sum. That is to say, finitely additive measures are automatically superadditive. Now, why is that? Well, let's recall from last lecture that we proved that measures are monotone. If you look back at the proof of that, there was nothing about countable additivity used there. And by exactly the same proof, finitely additive measures are also monotone. If A is contained in B in the field, then chi of A is less than or equal to chi of B. Keeping that in mind, instead of taking the countable union that we're interested in here, let's fix a large natural number, n, and consider the disjoint union of the first n of the AI. Okay. Now, we know that that is in the field. The field is closed under finite union. And also, critically, that is contained in A. A, the countable disjoint union of all of the AIs, certainly contains the first n of them. Well, therefore, by monotonicity, chi of that n-fold disjoint union is less than or equal to chi of A. However, chi is a finitely additive measure, and this is a finite disjoint union in its argument. Therefore, here we have the sum of chi of the pieces. Now look at that. For any n, the sum of the first n chi of AIs is less than or equal to chi of A. We can therefore take the limit as n goes to infinity. That limit exists on the left-hand side because chi is a non-negative valued function, and so this is a non-decreasing sequence, which therefore has a limit in the positive reals or infinity. And the right-hand side is not varying with n, and therefore we get the desired inequality in the n goes to infinity case. So, finitely additive measures are automatically countably superadditive. Let's just comment here that this inequality can be strict. And indeed, at the end of this lecture, we will see just such an example. But let's not dwell too much on the differences between finitely additive measures and premeasures. Let's barrel ahead and start to finally construct some finitely additive measures on the space that is going to concern us the most in this course, the real line. Now, the one sigma field we've already constructed and studied a little bit in some detail is the Borel sigma field over the real line, or more generally, over a metric space. It is not as complicated as some other sigma fields, and certainly Borel sets are much tamer than some of the wild sets that the real line contains, like, for example, the set phi in lecture 0, which presents problems when trying to measure it with a putative, rotationally invariant measure on the circle. Nevertheless, Borel sets are still pretty complicated. And so, let's, in the spirit of what we've been doing so far in this lecture, reduce our goal and study instead the Borel field. There are many Borel fields we could consider, but there's a natural one which will come up again and again, which I'm going to present here, and I'm denoting like this, because it's going to be generated by sets of this form. by half-open intervals. And to be clear, in this notation, we're allowing a to be equal to b. Well, if a equals b, the half-open interval from a up to a, open on one side and closed on the other, is going to be empty. Why is that? Because this set, open a up to closed b, means the set of all real numbers that are strictly greater than a, but less than or equal to b. If a equals b, there are no such numbers. By the same token, we also have that the set from a up to infinity closed for us really means a up to infinity open, because this is defined to be a set of real numbers, not extended real numbers. With that notation in mind, this set of intervals generates the Borel sigma field as a sigma field, but we're going to consider what it generates as a field. Well, let's take a first stab. Let's look at the field generated by those intervals. Certainly, it must contain unions of those intervals, since the field is closed under finite unions. Now let's think about those unions for just one moment. Suppose that I have a half-open interval here, a half-open interval here, another one here that overlapped it, a half-open interval here, a half-open interval that just abuts the last one. Notice that in fact these two merge together to form one bigger half-open interval, and the same is true for these ones, even though they just barely touched. And what we're left with is a disjoint union of intervals of this form. So any finite union of intervals of this form is actually a disjoint finite union of those intervals. Great. That collection of all finite disjoint unions of half-open intervals is clearly contained in this field. But guess what? In fact, it is equal. Now let's give it a name. I will call it the Borel field, denoted with this half-open interval sign. Now, why is this an equality? Why is this the field? Well, that's simply because you can check that the set of finite disjoint unions of half-open intervals is a field. Why is it a field? Well, we're just saying that it's closed under complement and finite union. It's already defined to be the set of finite unions. And so taking a union of two such unions gives us another such union. Therefore, it's closed under finite unions. If I take the complement of any one of these, I get something that looks very much the same. Keeping in mind that some of these intervals will be infinite at the edges, but that's all right. That's allowed in the definition. Hence, this object, this set of finite disjoint unions of half-open intervals, is a field that is contained in the field generated by the intervals. But the field generated by the intervals is the intersection of all fields that contain those intervals. And this is clearly one of those. So that gives us the reverse containment. And that shows that this is indeed an equality. We have identified the Borel field, the field generated by these half-open intervals. That's a nice, happy coincidence, but it's not really a coincidence. The fact that the field has this really simple structure owes to a particular algebraic structure in the way that these intervals interact with one another. And it's going to pay to abstract that a little bit and talk about yet another structure that is even weaker than a field, and that is a semi-algebra, or sometimes called an elementary class. A semi-algebra over a sample space omega is a collection of subsets that contains the empty set, is closed under finite intersection. So far, it feels like we're reproducing the definition of a field, but the weakening is with regard to the complement. In a field, the field would have to be closed under the complement, but in a semi-algebra, the complement of any set in the semi-algebra is not necessarily back in the algebra, but is instead a finite disjoint union of elements from the semi-algebra. The best example is the one we just studied, this quote-unquote Borel field, or rather, the set of intervals that generate it. This collection of intervals here is a semi-algebra. The complement of any half-open interval is not a single half-open interval, it's a disjoint union of two. Now note, from the definition, the whole sample space omega, which is the complement of the empty set, is a finite disjoint union of elements in S. That's always true in a semi-algebra. For the half-open intervals, the full space R is already a half-open interval, not just a disjoint union of one. What we saw happen on the last slide, where the field generated by the half-open intervals was nothing other than the set of finite disjoint unions of those half-open intervals, always happens for semi-algebras, and that's the proposition that we're going to prove now. If S is any semi-algebra, then the field that it generates is exactly equal to the set of all finite disjoint unions of sets from that semi-algebra. Let's go through a careful proof of this fact. To begin, let's give this putative algebra a name. Let's call it du of S, the set of disjoint unions of elements of S. We'd like to show that du of S is equal to the algebra, or field, generated by S. The first observation is that it's contained in the field generated by S by the same argument that we made in the Borel case a few slides ago. And this is simply because the field is automatically closed under finite union. And this just consists of some finite unions of elements from S. Similarly, S is of course contained in the set of disjoint unions of elements from S. And therefore, by a similar argument to before, to show that we have equality here, it suffices simply to show that this thing is itself a field. Because if it's a field that contains S, and therefore automatically contains the field generated by S, giving us the reverse containment to conclude equality. So we must show that this is a field. How do we do that? Well, we just have to revert to the definition and show that it is closed under finite union or intersection, which will be more convenient in this case, and complement. Let's start with intersections. Suppose that I have two elements, D and E, that are in the set du of S. That means that D can be written as a finite disjoint union of some elements AI in S, and E can be written as some finite disjoint union of some elements Bj in S. Well then, their intersection is the union of the intersections of the various pieces by De Morgan's laws. And that, I claim, is in fact in the set du of S, which is what we wanted to show. Now, why is that? Well, because S is, by definition, closed under finite intersection, each of these pieces is in S. And so to show that this union of them is in du of S, we simply need to show that this is a disjoint union. And that I will leave to you. The claim is that all AI intersect Bj are disjoint for different pairs ij. And that follows simply from the fact that the AIs are disjoint from each other and the Bjs are disjoint from each other. So this set du is closed under intersection of any two or any finite number. To show that it is a field, we need to show that it is closed under complements as well. And for that, let's take our arbitrary element d and look at its complement. The complement of d, which is a union, is an intersection of the complements. Now, by definition, right here, the complement of the set AI is itself a finite disjoint union of elements in S. And so what we have here is an intersection of disjoint unions of elements in F. But again, employing De Morgan's laws, we can rewrite that as a disjoint union of elements of S. And we can conclude, therefore, that D complement is in S. That shows that du of S is a field and concludes the proof. There is an abstraction of the somewhat geometric description that we saw of why the Borel field is indeed nothing other than the set of finite disjoint unions of half-open intervals. We will use semi-algebras in many contexts in the arguments in the coming lectures. One reason is that as relatively tame sets, it's easy to construct finitely additive measures on them. And better yet, once one constructs a finitely additive function on a semi-algebra, it automatically extends to a finitely additive measure on the algebra generated by that semi-algebra as follows. Start with a semi-algebra. You should think here of the set of half-open intervals. And suppose that we have a finitely additive function on the semi-algebra, like so. That is to say, it's a positive valued function with the property that if I have any set in the semi-algebra that is a disjoint union of two other sets in the semi-algebra, then that function chi is additive over that disjoint union. In that situation, chi extends automatically to a unique finitely additive measure on the algebra generated by that semi-algebra. And the way that extension works is the only way it could. The field generated by the semi-algebra consists of finite disjoint unions of elements from the semi-algebra. If you take any such disjoint union, the finitely additive measure on that disjoint union is defined to be the sum of the function chi on the pieces that are in the semi-algebra. Now, that formula must hold if this is going to be a finitely additive measure. But it's also clear that that formula uniquely defines the extension chi. And it is easy to check by the fact that it's defined as a sum over finitely many disjoint sets, that this is a finitely additive positive function. There is one subtlety, though. It's not clear that this formula is well defined. Any particular set in the field generated by the semi-algebra might potentially be decomposable as disjoint unions of elements from the semi-algebra in many different ways. And we need to check that no matter which decomposition we choose, the sum over that decomposition will give a consistent value in order to complete this proof. Well, let's see why that's the case. Let's suppose we can take a set A in the field generated by the semi-algebra and write it as a decomposition in these two potentially different ways. Each of the pieces EI in the first decomposition can be decomposed in terms of the FJs as follows. E is a disjoint union over EI intersect FJ. The reason for this is that the FJ union up to A, which contains all of the EIs. And therefore, EI is the union of all of its pieces in terms of the FJ decomposition of A. Well, by our assumption here that chi is a finitely additive function on the semi-algebra, that tells us that chi of EI is the sum over J of chi of EI intersect FJ. And that's because both EI and all of the terms EIFJ here are in the semi-algebra, since semi-algebras are closed under finite intersection. Well, then we can put this together with the putative definition of the finitely additive measure, and note that the right-hand side over there, the sum over I of chi of EI, is the sum over I and J of chi of EI intersect FJ. And there is a formula which is manifestly symmetric in the E's and the F's. Put another way, if we repeated this exact same argument, decomposing each Fj in terms of the partition of the EJs, we would arrive at exactly the same formula for the sum over J of chi of Fj, showing the desired consistency and well-definedness, and concluding the proof. Hence, finitely additive measures on fields generated by semi-algebras are tantamount to finitely additive functions on those semi-algebras. And due to the simplicity of the structure of semi-algebras, those are easy to come by. Let's use this observation to now construct a large number of finitely additive measures on the Borel field, which is generated by the semi-algebra of half-open intervals. The idea, which you'll recognize coming from elementary probability theory if you've seen it before, is to start with a cumulative distribution function. Start with any function f, defined on the reals, taking real values, that is non-decreasing. Since we don't care about total mass 1 in this case, our function f doesn't have to approach any value at infinity or minus infinity. It simply has to be real valued and non-decreasing everywhere. We can use this to define an additive function on the semi-algebra of half-open intervals as follows. For any half-open interval from A up to B, chi of AB is equal to f at B minus f at A. Now this is clearly non-negative. That's because f is a non-decreasing function. In order to show that this induces a finitely additive measure on the Borel field, we just need to show by the previous theorem that this function chi f is additive on the semi-algebra of half-open intervals. That means that if I decompose any half-open interval into two disjoint half-open intervals, the function needs to be additive over that disjoint union. So let's take a half-open interval. If I'm going to decompose it into two half-open intervals, it's going to look like this, where A is less than C is less than B. Now, chi f of AB, by definition, is f at B minus f at A. On the other hand, if I take chi f of each of the two terms in this sum, I get chi f at AC plus chi f at CB is equal to f at C minus f at A plus f at B minus f at C. And now we simply note, like a good calculus student studying the fundamental theorem of calculus, that we get internal cancellation of the middle term, and the result is indeed f at B minus f at A, matching what we needed. That shows that this defines a finitely additive positive function on the semi-algebra of half-open intervals, and therefore, by the proposition from the previous slide, it extends automatically to a finitely additive measure on the Borel field, the field generated by those half-open intervals, which consists of finite disjoint unions of half-open intervals. Great. For every such function, we now have a finitely additive measure. And you should probably recognize that the function is related to the measure from probability theory as the cumulative distribution function, if we were in the special case of total mass 1. Or you may recognize this from the construction of the Stieltjes integral, or Riemann-Stieltjes integral, from an undergraduate analysis class. But is it countably additive? That's the question we have to ask ourselves, because our ultimate goal is to produce a measure on the Borel sigma field, and that means we need a premeasure, a countably additive measure on the field generated by the half-open intervals. So, is this one countably additive? Let's take a look. Let's consider a half-open interval of length 1 from some point A up to A plus 1. That interval can be decomposed into a countable disjoint union of intervals like this. First, we take the interval from A plus 1 down to A plus a half. We put that together with the interval from A plus a half down to A plus a third, and so on down the line. That gives a countably infinite disjoint union. Now, if the Riemann-Stieltjes finitely additive measure that we developed on the last slide, in terms of this function f, were to be countably additive, then it would have to be true that chi f of that unit length interval should equal this sum, the sum of chi f on each one of those countably many disjoint intervals. Well, let's just calculate. By definition, chi f of the whole interval is f at a plus 1 minus f at a. And similarly, each of these terms is written here. F at a plus 1 over n minus f at a plus 1 over n plus 1. That is a telescoping sum, like we saw in the special case of two terms on the last slide. Let's write a few of those terms out to make it clearer. This is f at a plus 1 minus f at a plus a half plus f at a plus a half minus f at a plus a third plus f at a plus a third minus f at a plus a quarter, and so on. And like before, we get some internal cancellations. But how many? Well, as many as we'd like, decomposing it in terms of the first m terms in the sum and still having a tail. If we do that, those internal cancellations will give us that this sum is equal to f at a plus 1 minus f at a plus 1 over m plus the rest of the terms, n ranging from m up to infinity, of f at a plus 1 over n minus f at a plus 1 over n plus 1. Now, of course, the hope is that this will be small for sufficiently large m. But there's an implicit assumption there, an assumption about the continuity of f. In particular, the right continuity of f. Because what really happens here is that this sum, in the end, is equal to f at a plus 1 minus f at a plus, where this is shorthand for the limit as epsilon goes down to 0 of f at a plus epsilon, the limit from the right. Now we would like this to equal that in order for chi-f to be countably additive. And so we see clearly that chi-f is not countably additive if f at a plus is not equal to f at a. In other words, our function has to be right continuous everywhere to have any chance of this finitely additive measure actually being a premeasure. And notice, by the way, that since f is increasing, f at a plus is always bigger than or equal to f at a. And that means, with the minus sign here, that if there's any point where f is not right continuous like this, we do indeed get strict superadditivity of the finitely additive measure here, as I claimed could happen at the beginning of the lecture. Such Riemann-Stieltjes finitely additive measures are strictly superadditive in this inequality whenever that function f has any point of right discontinuity. Now, the deeper result, which we will come to in a few lectures, is that when the function f is right continuous, this does in fact define a premeasure, a countably additive measure on the Borel field. And even better, it extends uniquely to a genuine measure on the Borel sigma field. In the next lecture, we will begin the hard work, using tools like semi-algebras, of developing extensions from finitely additive measures to premeasures to measures.